It's okay. We are having a little bit of a technical glitch. In the meantime, I'd like to tell you all that at the end of each session, we'll have a 10-minute question quiz on the topics covered that day. That is, day two will have a quiz at the end as well. It will be conducted through a Google form, and the form will be active only for a very short span of time. So you guys have to be quick. Those who have the most correct and the quickest answers will receive some delicious swags from our sponsors. And the swags will be awarded on the basis of these quizzes. So keep an eye on the NeuRes channel on our Discord server because we will be sharing the link for the Google form right there once the event for today is over. Thank
Hello, am I audible? Can anybody give me a heads up? Okay, so sorry about that, guys. The internet situation these days. I'll get back to my presentation once again. So, like I said, today I'm going to be the speaker, and Shinjini will be accompanying me for the session. Now, if you've just joined us or had a great session with us yesterday, I hope to live up to the expectations in this session as well. So let's look at the topics for this session. So the first thing we're going to be covering is the overview of ANNs. Here we'll be going into the mathematical intuition behind ANNs and the mathematical explanation of how neural networks work. Then we'll go on to the forward propagation part, why we use activation functions, backpropagation, and in the end we have a hands-on session. This time it's in TensorFlow and Keras frameworks as well. So let's dive into the topic. So before I get on to the artificial neural network part, what I want you guys today is to have a notebook and a pen handy because we're going to be going through intensive math today. Now, don't worry if you are intimidated by the math. We'll be going through each and everything step by step. So I'll give you guys 5 seconds to get your notebook and pen ready, and by that time I'll just check my internet connection once again. So I think everything's sorted. Yeah. So for those of you who've just joined us, I gave an in-depth intuition or maybe an intuition on artificial neural networks. So I'd like to, give a recap to that intuition once again. Fuck. The internet's really pain in the ass today. Sorry about that. So those of you who just joined us, I was talking about the intuition of artificial neural networks I gave yesterday. So I'll just give a recap to that intuition once again. So let's start with this picture right here. So let's say these are the starting points, the input layers, and the output layer. These are the ending points called the output layers. Let's say these are islands that we are traveling from, the input layer islands and to the output layer islands. We can take various ways from going to the start to the end, and each route has different points, as you can see over here. Now, when we approach the destination, which is the output layer islands, we'll sum up all the possible scores and determine which island is the best one we're looking for. So it's like sending our, detection board teams and finding which island is the perfect one for the next vacation. Now, one interesting part to note here is that when the board teams approach the output layer, they come back to the input layer, and then we repeat this process, sending them towards the output layer and back to the input layer again and again. Now, coming on to the mathematical part. So diving into the maths straight away. So the input layer would usually be our training data, X, okay? And we'll be passing this data to the hidden layers. Now, like I said in yesterday's intuition example, these were our islands, but today we'll talk in simple deep learning terms, these are called our neurons. So what when we pass our data, you can assume that these arrows are some sort of weight operations we are applying to the data. And sometimes you also call them as weights. Now, a lot of time a question comes in our mind that why need weights? We use it for some features which I talked. It's like giving some power, and if a feature has more power, the output. So that's the reason we assign different sort of different weight to different features to get so these connections you can see right here. Can think them as a. So let's look at the notation over here. So this is the made layer. So when I talk about so like superscript L minus 1 into N superscript.
Hey guys, I guess Arsh's internet went out for a second again.
Is the screen visible? Hello, am I audible? All right. Sorry for this, guys. I had no idea my internet is going to be a pain in the ass. Shinjini, can you just tell me where I left off or where I got cut off?
You were telling about the hidden layers and stuff.
Oh, okay. So yeah, what I was talking about is the weight matrix, and so weight matrix would be of the size of the input layers, the previous layer, number of neurons we had in the previous layer, into the number of neurons we have in the current layer. So in this case, this would be 4 cross 5. Now, biases. What are biases? So biases are like intercepts added to a linear model. And so biases could be the intercepts added to a linear model. It is also an additional parameter in the neural network, which is supposed to adjust the output along the weighted sum of inputs to the neuron. So we have single biases for single neurons. This is how the whole process works. Don't worry if I got cut off, I'll come to this time and again. Now coming on to the notation part. This is really important. I want you guys to note everything down. Just a second, guys. I think I had some problem with my net, so I'll be going through the whole process again. Don't worry. Yeah, so I was talking about the topics for this session. I guess I've covered all this. So yeah, for those of who didn't attend yesterday's session, I want you guys to I gave some analogy related to neural networks yesterday. So I wanted to recap this analogy for you guys. So Let's start with this picture over here. So there are starting points called as the input layer, and the ending points called as the output layer. So let's say these are islands we are traveling from. So these could be the input layer islands to the output layer islands. We can take various ways from going to the start to the end, and each route has different points, as you can see. Now, when we approach the destination, we sum up all the possible scores and determine which island is the perfect one we're looking for, right? So given the three, we could select any one. So it's like sending our detection board teams to find out the perfect island for our next vacation. One interesting part here is that when the board teams approach the output layer, they come back to the input layer, and then we repeat the whole process, sending them towards the output layer and calling them back to the input layer. So that's all about the intuition or intuitive explanation behind this. Now let's come to the deep learning part. So let's say, so the input layer, usually we pass the training data from the input layer to the all over. So we propagate that training data all over from the input layer to the output layer. Now let's say we have some data, and in simple deep learning jargons, these islands are known as neurons. There's also one thing I'd like to mention. If you could see these connections, you could think of these connections as applying certain weights to our input data given the features. So features is something I explained yesterday. So you this the question could come in your mind that why do we need weights at all? So we use it in the sense of power to a certain feature or sample. So if a feature gets a high value of weight, then that feature will have a great impact to our outcome. So by giving different weights to different features in these, so these connections could be the different weights, and to different features would be the input data, we can train our model for a better prediction. Then comes the bias part. So why do we need a bias? So the bias is like the intercept added to a linear equation. You just change the position, but the thing remains the same. So it's like an additional parameter in the neural network, which is supposed to adjust the output along with the weighted sum of inputs to the neuron. So let's look at the notation part here. The input layer is of X neurons. The hidden layer have N superscript L. Now, one thing about notation I want you to focus on is that whenever in something, when I'm explaining something like this, whenever anything is written in the superscript, it is the current hidden layer I'm talking about. So the NL would be the current hidden layer I'm talking about, and then the output layer has Y neurons again. So let's see, let's look at the weights here. Now the weights, so this is the size of the weight matrix. Now what according to you should be the size of the weight matrix? Obviously, it should be the possible connections we have over here. So the input layer has 4 neurons, the output layer has 5 neurons. We need to make 5 connections from 4 neurons. So that's what the weight matrix size is. It's simply 4 cross 5, because we have 4 neurons in the input layer and 5 neurons in the layer we're talking about. So that would be the size of the weight matrix. Next comes the bias. Now, to each neuron we just add a single bias. So for each neuron we'll be having one bias. So in our case we'll having 5 biases in totality. Now, next comes the part where I want you to look at some of the notations here. Like I said, do have your notebook and pen with you at all times during this session, because we'll be going through a lot of math today. But don't be intimidated by that fact, but it'll be easy. So let's come on to the first notation here. Like I said, the superscript is always the current layer we are talking about. Now this WM subscript M comma MN, what is this? So this would be the weight from neuron N of layer L minus 1 to the neuron M of layer L. Now I'll be explaining this with the help of a diagram in the next slide. I just wanted you to have a look at this and note this down on your notebook. This would be the neuron of that layer. This is just the mth neuron of that layer. This would be that bias for that layer. Now we're talking about single neurons here. Now when we talk about all the layers, we use matrices and vectorized equations, which I'll also be coming to at a later point in this webinar. So I'll give you 5 seconds to absorb all these notations and write them down, and then we'll proceed forward. Yeah. So the next part is the forward propagation part. Now, in our analogy, our both teams are going from the input layer islands, as I must say, to the output layer islands. So what they're doing, they're moving forward, right? So that's what we are doing with our data. We are propagating this data forward from this part to this part. This is the textual meaning of the word forward propagation. Now let's look at the process of forward propagation. So let's look at what is happening in this neuron, A4. So superscript of 2 means we are talking about the layer 2, and A of subscript 4 means we're talking about the fourth neuron, which is being 1, 2, 3, 4. The whole process till A4. Let's discuss about that process. So as you can see, I told you about the connections. These connections are usually associated with the weights. Now I explained you about the notation of weights, that MN notation. Let's have a look at it once again. Now W of MN is usually the weight from neuron N of layer L minus 1 to neuron M of layer L. In this case, W of 4, 1. So M in our case is 4, and it's coming from 1th neuron, the first neuron in layer L minus 1. So this would be that, which is multiplied with this. So connection is the weight and multiplied by the output of this neuron A1, so of layer 1. So this is the first portion. Now let's talk about the second connection, A2 to A4. Now the output of A2 would be multiplied with the weight is of, we're talking about the fourth neuron, so M would be 4, coming from the second neuron of layer 1, so that would be 4 2 into A2. Similarly, we talk about the third neuron of layer 1, so that would be weight of 4, that is M is this, 3 is this, and the output A3 multiplied. And then similarly for fourth one, that is weight of fourth and to the output of fourth, and then we multiply it with the output of this layer, this neuron. And finally, we add a single bias to that neuron. Now, one exercise for you guys is that you can calculate the whole process for A3 and A2, now which you can do in your own free time. Let's now that we've computed this part, remember in yesterday's session, we told you that you need to apply an activation function to it to make your to introduce to highlight the non-linearities in your data. Now, while we use activation functions is something we'll come on to later in the session. Right now, you just think of it as you've done all the computation till here. You apply that activation, and then you propagate this neuron forward and can do the same process over here in layer 3. So this was all about forward propagation. Now let's come to vectorized equations. Now here it's a very raw form of writing the whole process. So in vectorized equation format, we're just denoting the whole process in a form of vector notation. So when I talked about all these four ways here, that is W of 4 1, W of 4 2, 4 3 4 4, I can represent them as a vector, as a column vector. So this would be the here. So this is our column vector, W of 4 1 4 2 4 3 4 4. Similarly, I can represent the output of all these neurons. Here, A1, A2, A3, A4, I can represent them as a column vector, which I'm doing here. And then I can do, the multiplication of two vectors together. And then I add a bias vector. Sorry, the bias, not the vector, because I'm talking about a single neuron here. So this would be a constant value. Now, if I'm talking about the whole layer, so all the operations should be considered. Here, I was just talking about A4. Now we need to talk about A1, A2, A3, A4, and A5. So we do all these operations for all the neurons. So in this case, our weight vector would be a matrix. So the first row, so this here could be substituted before this here. The whole column for that fourth neuron, this one, this column is for the first neuron, which is A1. Similarly, for A2, we have this column. For A2, we had this column, and so on and so forth till the fifth neuron. And now, since we are talking about all the 5 neurons, we should have a weight vector, column vector for the biases as well, because now it's a column vector because it's 5 values together. in the whole layer. So even the biases are represented as the column vector here. So this would be the whole layered operation. And this is our layered notation for that. So the next part is why we use activation functions. This is something Shinjini will be covering. Over to you, Shinjini. Thank you for my part.
Yeah, so activation function is something we had covered yesterday. It is the function that we apply after doing the linear calculation, which Arsh just talked about, which is the z that we spoke about. Now, after knowing that equation, we can finally understand that why we need activation functions. Now, applying no activation, we will first see that what happens if we don't apply any activation. Not applying any activation is essentially known as the linear activation. So if we do not use activation, this is the first layer that we saw here, the first layer. We calculate the activations of the first layer by multiplying the weight matrix of the first layer with the inputs and added with the bias. For the second layer, it's the same process that we saw, multiplying the weight matrix with the input to the second layer plus the bias. This term right here is the substitution for A of 1. If we use the same old distribution law that we know and open the square brackets, we get that we multiply the two weight matrices, we get A of 0 and this term right here. If you look closely, you can multiply these two weight matrices and get a single weight matrix because it's just weights, no matter how many, and you are multiplying them. Similarly, if you look at the second term, these last two terms, these are just weights and biases, which can again be taken as a single bias. Essentially, if you look at it, it's in the form of a straight line, y equals mx plus c. So what we can conclude from this is that no matter how many layers you add, how many times perform the same linear calculation of z equals that wa plus b, it will always be in the form of straight line, which doesn't help much for our case. We want to divide different forms of data. We want to divide them into a lot, n number of categories maybe, or maybe predict some value. And dividing with a straight line doesn't really help us. So here therefore we introduce what is called the activation functions. Activation functions are non-linear, as we saw in the graph yesterday for sigmoid or tanh or ReLU. They are non-linear, so in turn, they introduce non-linearity into our neural network. Now, introducing non-linearity increases the scope of the network. It increases the scope and it lets the network find out more complex patterns and more correlations between the input and the output so that it can predict what will be the outcome of a new input in case we provide it. I hope it's clear now that why we use activation functions. And so now that we have reached why we use activation functions, we are done with the forward propagation part. After that, we have the backward propagation. So yesterday we had talked about that we first propagate the input data through the network, and then we let the neural network know that what is the error, how wrong is it, by comparing it with the output provided in the data set. Now, after letting the neural network know how wrong it is, we have to actually correct it. We have to let the neural network correct itself. And that is done by the backpropagation. I'm sorry, that is not done by the backpropagation, that is done by the optimization algorithms, one of which is the gradient descent. If you remember gradient descent, what did we do in gradient descent? We started from the topmost portion of the cost function, that is the maximum value of error, and went to the minimum cost function. so that the error is the lowest possible value. Now to perform gradient descent, we have to calculate the gradient first. And the gradient is calculated by this algorithm, which is the backpropagation. Now, first, what we need to know is, what do we mean by gradient? By gradient, we mean that we calculate the partial derivative of the cost that we have got with respect to each of the weights. So I'll repeat again, which is the partial vector of the cost function with respect to each of the weights. Now, this diagram right here is a perceptron model, which is just a single layer. Here you can consider the x1 till x3, these as the input layer, z and a as one neuron. We have just split the function of linear calculation and the activation function into two. So if we look here, we can find out the weight. We cannot find out the derivative we asked for, that is dou c by dou w1 directly. Therefore, we use something which is called the chain rule. Now, these may be a lot of equations, but I'll explain it. Dou c by dou a, that is something we can calculate directly, since this is the output layer. After that, we have dou c by dou z. We expand this dou c by dou z into these two terms, and so we get the value of dou by dou z. This is something we already got. So a by dou z is something we calculate, because if you remember here, right here, a is a function of z. So this direct. After reaching this point, what we that is the grades c by w1, expanding using the chain rule. We use this term right here with by dou w1, which is something we can again calculate directly, because to calculate z in the first place, we used all these three weights. Since w2 and w3, they are at the same level of the neural network, that is in the same layer, they can be calculated in a similar fashion. So here we have just w2 instead of w1 and w3 instead of w1 again. So I hope this part is clear. If yes, then we'll move on. I'll just give you a second to look at the slide. So now that we have done the backpropagation chain rule for a single layered perceptron model, we move on to this one. This is the same neural network that we used for the forward propagation. The same neural network that we use for the forward propagation. Now here, we will do the backward propagation for just one weight, a single weight, the weight W43 of 2, which is again the weight that goes to the fourth neuron of the second layer, the fourth neuron of the second layer from the third neuron of the previous layer, which is this one. So we want to find the gradient for this weight right here. To do that, if we look back at the equations, I hope you have noted these down, because it will help you a lot. If you go back here, if you look back at those equations, these two equations are essentially the same, except we have added the notations that which layer and which neuron. One of three is this one, our output layer. This is something we can calculate directly, because again, the output layer. This is something I just told you, I just mentioned in the previous slide, we can calculate this directly because A is just Z after applying the activation function. After that, we can reach this weight right here, W14 of layer 3. For that, we use the value we already found out right here, and we multiply that with this term, which we get from differentiating the z here, z of this neuron with the weight that we want to find the derivative of. If you notice a little more here and here, you'll find that you get a pattern. It's essentially the same equation, just that the subscript and the superscript, they change. Now, just the extra step here is that we need to find this derivative that is with respect to the previous layer 2, the fourth neuron of layer 2. That is something that is again expanded. This is a chain rule again. It is expanded, and these terms can be found out directly, and hence we get this value. If you look at these two equations, these are essentially the same as these, as I told. So this is how we get this weight, which is the one connecting going to the fourth neuron of the second layer from the third neuron of the previous layer. So I really hope it's clear just here. If not, you can ask your questions in the chat box. There will always be someone to clear your doubts. Now, obviously, this is too much work calculating all of this and this is just for a single weight that we found out. And we want this for all of the weights so that the weights can correct themselves. For that, we use the vectorized form. Now, before we move on to the vectorized form, you guys need to notice something. Here, A is the G of Z. Therefore, we can write it as G prime of Z. Here, Z with respect to W of 1. If you go back to this slide right here, if you partially differentiate Z with respect to any one of the weights, partially differentiate, what you are left with is just a single input value. So here we have the same thing. This is essentially just A. One last thing, Z with respect to A of the previous layer. We go back once more. If we differentiate Z with respect to a single input, we are left with one weight, because in partial differentiation, all the other terms are considered as constant, as we know. So once we know that, we can move on here. This is quite a concise form of all that we went through. So here we have D of A. We just denote dou C by dou A as dou A and dou C by dou Z as dou Z, and so on. So if we see dou of Z, it is dou of A by G prime of Z, just right here. Dou of Z equals dou of A G prime of Z. dw, dou of Z multiplied by the vector, the input vector of the previous layer that's coming, the input vector. That's what we found out here, that was A. And here it was W, right here. To find the derivatives with respect to the previous layer inputs, that's previous layer activations, we multiply it with the dou Z of that layer and the weights that's coming from it. Am I audible?
Yeah, Shinja.
So I hope all of this was clear, because it was a lot of math. After this, I really think we need a break. You can head over to our Discord outer circle server for any questions you have and connect with us and take a 5-minute break. So welcome back, guys. I hope you are re-energized now after all that math. The worst is behind us, so don't worry anymore. Before we move on to the hands-on part, that's the practical application of ANNs, there's a small topic that we need to know. It's random initialization. Now, random initialization of what? The weights. Naturally, if you think of it, the first thought that comes in mind would be that the weights must be initialized as 0, as it's done in all programming languages. That's the default thing. But if you think enough, if the weights are 0, we end up with it happens that all the neurons do the same calculations and it ends up with the same results. In turn, there is no efficient backpropagation. The gradient turns out to be 0 or constant, basically meaning that the neural network doesn't learn anything. To avoid that, we do random initialization, which is that the weights are initialized randomly, or according to there are some other methods of initializing it, which we are not covering here. But this is just something that you needed to know. It's not, never 0. We never start with 0. So after we have completed the whole forward propagation and backward propagation process that is going through the network and back again, telling the neural network what is wrong with it. We move on to the summarization part. We will summarize once that what happened. Ash will take over from here.
Yeah, so thank you for that, Shinjini. Now that we've completed all the processes, I'd like to just a second. Yeah, I'd like to explain what the whole training process looks like. So, as you can see, we start with some kind of labeled data. It could also be unlabeled to some extent, and I'm not getting into that. And the whole point here is that you compare the predictions of your model to the reference, which is your labels finally. So you start with the inputs, forward these inputs to get the prediction, and the network being an artificial neural network. Now, once you get the predictions, you compare the prediction values with the actual labels. Now, you compute the errors, which is based on the loss function we talked about yesterday. And once you've computed the loss, you end up taking the gradient of the loss. And for each layer, starting from the and you compute the gradient of the loss for each layer, starting from the back to your input, like starting from the output layer to your input layer. And then you back propagate these errors, which is basically the gradient of your loss. And then finally, you update the connection weights. So this is basically the training process. I would definitely recommend you to check this out in more detail. Moving forward, now let's prep up a little bit for the hands-on sessions. So our hands-on session is going to be in TensorFlow with Keras. So before moving on to TensorFlow, let's talk about what a tensor is. So what a tensor is basically, so from a programming perspective, a tensor is a multi-dimensional array that has the ability to be run on a computer. Now, like I said yesterday, our data is usually in a form of a multi-dimensional array. So that there's that. And from a mathematical perspective, a tensor is a generalization of a scalar vector in a matrix. So essentially, a vector is a one-dimensional tensor and a matrix is a two-dimensional tensor. Now, let's start with the basics of. So this is what Tensor is, and TensorFlow is just a free and open source library for machine learning, which allows you to do all the back propagation and all the daunty looking stuff which Shinjini had explained earlier. This type of programming is also known as differentiable programming, and so that's how I guess the TensorFlow's name came. The tensor flows from the input layer to the output layer and back to the input layer once again. So that's the name TensorFlow. Now let's look at what. Let's start with the basics of tensor as to how you can represent data. Okay, so as you can see, the tf dot constant here. I thought it's good to know, especially when you're, when you're deep into the learning stuff and you try to replicate a research paper or represent some custom data, you should know what TensorFlow is and how to work with it. So constants in TensorFlow are represented by tf.constant, and then you pass in any kind of a Python structure like a list of lists given over here. And so as you can see, the basic thing about TensorFlow is that you can interchange TensorFlow tensors to NumPy arrays, which I think is the biggest advantage for us, because we know how computations work in NumPy. And the data type, as you can see, is given float 32, which simply means that we are representing floating point numbers. The next thing is t.shape. Then we got t.d type as well. It's as similar as NumPy. The t.shape thing represents the shape of the tensor, which in this case is 2, 3. And so that's about, and it's, as you can see, it's really similar to NumPy. Now comes the tf.variable. Now in so it's a variable. So in tf.variable, you can pass in any single or multi-dimensional tensor as necessary. And as you can see, I've passed this bit here, which is of the shape 2, 3. The next thing is you can check your D type and shape. And then, like I said, converting from a tensor to a NumPy array is really easy. You just do t.numpy. And that's as easy as it sounds. Now, when you're modifying a tensor variable, you cannot equate it to a number. Okay, so you need to assign, you need to specify the index and then assign the value using this method here, which is t of index.assign, and I'm assigning 99 to the position 0, 0. And as you can see, the place where it was 1 before, it's 99 right now. And the next thing is indexing. I won't go into indexing. Indexing is really similar to NumPy. Just look at the 3 dots here. The 3 dots simply mean all the columns or all the rows, and it's just something you need to know, and I won't get into the depths of it. The next thing you can perform with a tensor is the basic operations. The t is t plus 10. You can square a tensor. I'm not getting into these operations as well because you might rarely use them. But so tf.square would just give us the square of all the values in our tensor. And you can also do an np.square. That's how, a symbiotic relationship tensor and NumPy array have. And then at the end, we're just multiplying the two tensors. The @ is just matrix multiplication. And the transpose function, just, if you've done the high school math, you know that the column of first matrix should be equal to the row of the second. Next slide, please. Yeah, so like I said, you would never be using TensorFlow core, but since I thought you should know about it. What you would actually be using is Keras, with the TensorFlow's integration with Keras. Now, what is Keras? Keras is a high-level API that uses TensorFlow as backend. It provides an API to write Python code for building neural networks. It's as easy as it sounds. So you don't have to do all the forward propagation. You don't have to hard code it. Like previously, people used to do it in C++. So you can imagine the pain they used to go through. Now it's so easy that you just need to do tf.keras.layers and you have your first layer. You pass in your data and you propagate your data. That's how easy it is. Now there are 3 ways to create models in Keras. The first way is the sequential model, which we'll be talking about today. Sequential model means nothing but sequentially passing on our data, which is single input, single output, and stack of layers, which means you pass on your data to the neural network layer, and then you propagate it. So sequentially, the data flow is sequential. Now, the functional API is actually used in most cases and supports arbitrary model architectures. This is something we're not covering today. And this is something which you will rarely use. One use case which I came across when I was doing a course, and don't worry if you don't get this. There's a model architecture called the ResNet, and you'll be covering this when you attend tomorrow's session on CNNs. So when you hardcode ResNet, you might use functional API. Now, don't worry if you don't get this. You can always look up to the internet. The last thing is model subclassing. Now, if you want to implement a custom model, right? So when you're doing a sequential model, so for each layer you have one activation function for all the neurons. Now, what if you just stand up one day and say, I want different activation for different neurons? So that is the time when you make a custom model for yourself, and that's when you will be using model subclassing. And custom training is something we won't get to in this session as well. So that's all about the prerequisites of the hands-on session. And I hand over to Shinjini for the hands-on part. Thank you.
Yeah. So after Arsh is done with the uh, basics of TensorFlow and Keras, we'll move on to the hands-on session. I'll just take a minute. Yeah, sorry about the delay. In this hands-on session, we will train a dataset called the Fashion MNIST, which is a quite well-known dataset used to teach beginners. Now, what we just import our libraries and look at the versions here of our libraries. We move on to what is the Fashion MNIST. Now, the Fashion MNIST consists of, as written here, 60,000 examples and a 10,000 set size of test set. Now, what is a training set and a test set? Here, training set is the data set that the neural network looks at repeatedly, as we say, like trains on, learns from. And the test set, which contains 10,000 examples here, what the test set does is it gives us an evaluation. It tells us how the neural network is now that after that we have trained. After training, we pass the test set through the neural network so that we know what is the accuracy of it. In the Fashion MNIST dataset, each of these images is a 28 by 28 grayscale image, that is 28 by 28 pixels, and they belong to 10 classes, that is 10 classes of fashion apparels like t-shirt or boots or like that. We will see what they are in a while. Here we just load the data. We divide it into the train set and the test set. X is the input data, Y are the outputs, that is the target labels as we call it. If we see the shapes of the test set and the train set consists of 60,000 images as mentioned earlier. Each image is 28 by 28, and in the test set we have 10,000 images, each 28 by 28. This is just an example of how the images are in the training data set. What we do here is we normalize our images. If you know anything about computer vision, each pixel has a value from 0 to 255. So by dividing by 255, we reduce all those values into between 0 and 1. We just do that because the neural network likes values between 0 and 1. It's easier to work with them. Why train? These are our target labels. That is, each number denotes one of these labels, that is t-shirt or trouser, pullovers, whatever. These are the labels for the respective numbers. We print one of these labels, that is ankle boot. Okay. We just view our dataset once again using our matplotlib and set our random seed, which is to set the same data every time. Now we build the actual neural network. tf.keras.models.sequential is something we use to build the sequential model, as Arsh just mentioned, that is single input and single output. What single input and single output mean here is that the input is from a single layer and the output is from a single layer. every layer is connected to just one other layer as input or output. Then comes the flatten. Flatten layer just takes our input and converts it into a row vector. That is, since our images were 28 by 28, it will take the 28 by 28 image and take the pixel value of each pixel and expand it into a row vector. So we will have 784 inputs. We use the dense layer to finally define our hidden layers. We use the dense layer, and here we have 300 neurons. 300 denotes number of neurons. Activation is ReLU, as we have discussed yesterday. We define a second hidden layer. This hidden layer contains 100 neurons, same activation ReLU. The last layer contains 10 labels, that is 10 neurons, because we have 10 labels here, as we saw right here. The activation is softmax, which, as discussed yesterday, gives us the probability of each neuron being the answer to our input, that is, being the category our input belongs to. This is how we define a model, and we can add more layers, and there are a lot of other types of layers. We'll not get into that here. We can add more here, but we'll keep our neural network simple. After refining the model, we have to compile it with the loss cost function, that is loss here, and the optimizer algorithm, that is how our weights are updated, that is called the optimizer. Loss here is the sparse categorical cross entropy. Now, the sparse categorical cross entropy is something that is we talked about yesterday. That was basically the categorical cross entropy. I'm sorry, just the cross entropy for choosing one of n classes. Sparse categorical cross entropy is used when we have integer labels, as we saw right here. Integer labels. In case each of these labels were replaced by a single vector, which had 10 digits, with all zeros and one of them as 1, denoting which label this sample belongs to. That is, in case of 9, it would have been 8 zeros, then 1, then 0 again. That is called one-hot representation. One-hot encoding. If we had one-hot encoding, we would have used the categorical cross entropy. But since we have introduced the sparse categorical entropy, there's something else which is binary categorical cross entropy, or binary cross entropy, which is used for binary classification, 0 or 1. This is the SGE, the stochastic, as we had discussed earlier. This right here is a learning rate, which is basically 10 to the power minus 3. And in the metrics, we include accuracy, which means that while training, the code will display the accuracy it has on each step. Model.summary prints the summary of our model that we had built, 1 flattened layer and 3 dense layers. 784, as I had said, that is after expanding the 28 by 28 image. 300 neurons in the first hidden layer. In the second hidden layer, it's 100, and finally in the output layer, we have 10 neurons for the 10 labels. So we have defined our model. We have defined the cost function it uses, the optimizers it uses. We will now actually start training. Now, after all that math, this must be a bliss. It's just 4 lines for training. And this does all of that math we saw in today's session. We'll go through each of the terms, what these means. Firstly, epochs. Epoch is going through the dataset once. If we go through the whole dataset once, perform forward propagation and back propagation, that is, in our case, all 60,000 images, we perform 1 epoch. So like that, we perform here epochs is 20, so we perform 20 epochs. Batch size. Now, batch size is how many samples we take at a time. Now, though we have 60,000 samples, we take 32 samples, pass them, forward propagate them, backward propagate them, display the loss as we can see here, and accuracy, and move on to the next batch. That is, we perform 60,000 by 32. We have 60,000 by 32 batches since each batch contains 32 images. If you train this thing, we will provide you the notebook later. If you train this, you will see that while training, the loss and accuracy keep on changing. That is because it's calculating the loss on each batch of images. That's why we have 1688 by 1688. That is the total batch number. The next thing is a validation split. Now, I talked about the train set, which is used for training, the test set, which is used after training. Now, validation set is something between them. You can consider it between them. It is basically used to adjust our. Now, while we the train data set is passed through the network, and after one epoch, the validation data is passed through it, and we see the accuracy on that data. Looking at this accuracy, we can take a guess at how well the neural network is doing while it's training. So this is just a way of checking the accuracy while we are training, not after the whole thing is over. Also, things like epochs, the batch size, and the learning rate, as we saw here, these are called hyperparameters. These can be tuned, that is adjusted after with the help of validation set, because we see while training how it is doing, how the network is performing. So in our case, we performed 20 epochs and finally got an accuracy of 85.29% on the test set and 84.92 on the validation set. Since these two accuracies are close, it just means that the neural network is performing as promised. Often it happens that it performs really well on the training set and doesn't perform quite well on the validation set. It just means that the network is learning only from the training set and is not generalizing to other cases that may happen. But here, no problem. Now, this accuracy can be increased to above 95% if we use convolutional neural networks, which will be covered on 19th session, the session we have on 19th March. So you can try that yourself after you learn CNNs. After training, we look at the plots. The plot, the blue lines denote the losses, that is the values we get from cost function. The red lines are the accuracy. So as our error keeps on decreasing, that is our loss keeps on decreasing, the the accuracy keeps on increasing. But, obviously, if the error decreases, the accuracy will increase. We finally just print the encode that the answers that we have got, that is the values that the neural network has returned after passing the test set. These are our predictions. Since we had 10,000 test samples, we have 10,000 row vectors, each of 10 values. The 10 values denote the probability of each label being true. So using the argmax function, we choose the index which has the highest value. That gives us our labels. Now, obviously, we cannot sit and match each label with our training set, like what we had, each label from the neural network with each label provided to us. So that is, for that too, we have functions, which is provided by the sklearn library. We have just calculated the accuracy here, which is 83% here. There are quite a lot of other accuracy metrics, which we are not going to cover here, but we have mentioned them for you so that you can search them up and look what they are. So that's it for today's session. We will be providing you the The link for the Discord server will be provided in the chat box, and you can join the Discord server, look at the NeuRes channel, and find the link for the quiz. Thank you.
Okay, thank you so much for the wonderful session, Shinjini and Arsh. It was pretty insightful. Everyone, since the session has ended, we'll have a 10-question quiz on the topics that were covered today. It will be conducted from the Google form that we told you about earlier, and the form will be active only for 5 minutes. So those who are get the most correct answers and are the quickest to answer, they will receive some delicious swags from our sponsors. So please head to the Discord server for the quiz. And lastly, I'd like to thank the sponsors for NeuRes, as well as kindly avail these coupons for all. This is for all the participants. Thank you everybody for joining us today. We'll see you at the next session.